Three, two, one, go. All right. Welcome back this morning. Well, today we're going to be talking about the next part, which is the seafloor spreading. And this is assignment number 14, I believe. Now, when we're looking at our state standard, what it's asking us to do is to analyze and interpret data on not only the distribution of fossils, in other words, where fossils are spread throughout our world, and rocks, but also to look at the continental shapes, how those things match up, which we saw before. But today we're really going to look at this. We're going to look at the sea floor, which is the bottom of the ocean, the structures that help us provide evidence that possibly in the past, these massive continents have been moving, or that our Earth, the ocean floor itself, is actually moving. It's not just staying still. It's actually moving. So that's our big target for today, is to kind of understand seafloor structures and providing it with that evidence to see, is there actually proof that we could say maybe it is happening? Well, let's pick up where we left off last time from that continental drift. And that is, we finished the continental drift yesterday. Now we're going to move into this idea. We had this claim as we ended yesterday. And the claim was, Alfred Wagner said all the Earth's land was once joined together and since has moved apart over time. That was a claim that Alfred Wagner produced, and the evidence that he collected, at least the three main types, was he said, look at the shapes of the continents. They actually fit together on a map, and there's actually land features, mountains in South America and Africa, which are oceans apart, that fit together and are actually the same. There's coal deposits in Europe and in America that fit together. And he said, that's not coincidence. That's pretty amazing that we can see that those things actually fit together and that the shapes of the continents seem to fit together as well. That was one of the evidences he provided. Another thing was, he said, look at the fossils that we see on these different continents matching up. Even though South America and Africa are separated by the Atlantic Ocean, both of those continents have a Mesosaurus, which is not a ocean swimmer by any means. It's more like a little crocodile. It wasn't built for going across the ocean, nor would it have its significant other that it could create babies with and produce this life with. So how it would go back and forth over an ocean just didn't make sense. These fossils showed that this land probably was pushed together at one point, and that this animal probably went around this entire area, and then it's since died and the land is separated. And then a third one is changes in climate, like Antarctica having palm trees. Antarctica's South Pole. It's freezing cold. There's miles worth of ice down there, but you're telling me there's palm tree fossils under some of these sheets of ice that they found? So that shows that maybe Antarctica, though it's frozen right now, in the past was probably warm. Maybe it was moved up more towards the equator so that it was actually warmed up. So the shapes of the continents, the fossils that we find on these continents, and the changes in the climate. Some places that are now cold in the past show that they were warm. Same thing with Africa. It showed that now it's kind of a milder warm in South Africa, but in the past it had glaciers on it. So that shows that probably it's been shifting around. The reason for it? Well, Wagner still couldn't come up with the reason. He just came up with the claim and the evidence, but he doesn't know the reason. Bad news. Sad days for Alfred Wagner. In fact, Alfred Wagner produced a book, Origins of Continents and Oceans, stating his claim of continental drift. The leading geologists at the time, a lot of them did not believe that he had really anything, because they couldn't provide the mechanism. How would this work, Alfred? How in the world would massive amounts of land move like this? And in fact, he pretty much died without ever knowing that people started to pay more attention to his theory. But bad news, people didn't believe him after he submitted his book. Some people thought he was just a fraud. Wagner's hypothesis is rejected. Wagner attempted to explain how continental drift took place. He suggested that the continents plowed across the ocean floors. Unfortunately, Wagner could not provide a satisfactory explanation for the force that pushes or pulls the continents. Because Wagner could not identify the cause of continental drift, most geologists rejected his idea. Poor Alfred. Poor Alfred Wagner. The dude is just not doing it. But here we are. Still, there is more. Geologists' thoughts at the time, that's on the left-hand side over here. Geologists, they wanted for them to accept continental drift, this idea that Wagner had, they'd have to have changed their ideas about how mountains formed. In the early 1900s, many geologists or people that study the Earth thought that mountains formed because Earth was slowly cooling and shrinking. According to the hypothesis, mountains formed when the crust wrinkled like the skin of a dried up apple. That was their thoughts. Versus Alfred Wagner's thought was that if these geologists were correct, then mountains should be found all over Earth's surface, shouldn't they? Shouldn't the whole Earth be shrinking like a dried up apple? But mountains usually occurred in narrow bands along the edges of continents. Wagner developed a hypothesis that better explained where mountains occur and how they form. Wagner proposed that when continents collided, their edges crumbled and folded. The folding continents push up huge mountains. Well, it wasn't until this word mid-ocean ridges came about. You see, the East Pacific Rise is just one of the many mid-ocean ridges that wind beneath the ocean's surface. In the mid-1900s, scientists mapped the mid-ocean ridges using sonar. A lot of times this was used in the World Wars because during the World War, people were mapping out the oceans looking for submarines from Nazis and all sorts of things because that was part of the thing. As they went through the oceans looking for all these secretive little submarines that people were sneaking around in. And in that, they actually started to map and sonar map a lot of what the ocean floor was. Sonar, if you don't remember, is a device that bounces sound waves off underwater objects and then records the echoes of these sound waves. So when it bounces a sound wave off, the sound wave echoes back up into the top, and pretty soon you've got a distance, basically, is what you can determine as how far it is, and then you can kind of see where it is as far as the depth goes. By the time that it takes for the echo to arrive, it basically tells you the distance to an object. We use the same thing. This is what really helped us in World War II, because when people were coming through, the Nazis specifically, and bombing lots of parts of Europe, London, and all sorts of places, sonar was a huge part because it actually allowed us to find out when these planes were coming kind of ahead of time. We would set out these kind of radar in a sense. But yeah, sonar was used in a lot of different ways, but because of that sonar bouncing off these waves, now we started to see these mid-ocean ridges curve like the seam of a baseball along a sea floor is what some people have described this as. And in fact, you can see it right here, that this area coming down right through here, this area looks like the seam of a baseball. That's a mid-ocean ridge. They extend into all the Earth's oceans. And figure 15, that picture right below, shows the location of these ridges. Most of the mountains in the mid-ocean ridge system lie hidden under hundreds of meters of water. Not out in the plain sight for all to see, but actually under the ocean. Well, in a few places, the ridge pokes just above the surface, but not too much. However, for example, the island of Iceland is a great one to look at. It's part of the mid-ocean ridge, and it rises above the surface of the North Atlantic. And right here, it's an active volcanic area. It's got steep-sided valley as it splits into some of the mid-ocean ridges. This is a part where this mid-ocean ridge actually goes above the water, and we can see it. And it's a little island called Iceland where people live. Big thing that we're seeing all the way through these turquoise-looking, kind of green-looking ridges that wrap all the way around our Earth is this right here. We're seeing that from the depths of the Earth, lava is coming up through, magma, and it's pushing away in different directions the ocean's crust, which makes sense that if you look at this mid-ocean ridge, it would be pushing away in opposite directions South America and Africa. If you reversed it, it would bring them together and they'd fit like a puzzle piece. And then our fossils would line up and all sorts of things would make sense. So this idea of a mid-ocean ridge existing was found out by the sonar. As they were mapping, they said, hey, there's a huge mountain range in the middle of the Atlantic Ocean. I think this mountain range might have something to do with Alfred Wagner's theory of continental drift. So seafloor spreading continues. What is seafloor spreading? Well, Harry Hess, as another person, an American geologist, was one of the scientists who studied mid-ocean ridges. Hess carefully examined maps of the mid-ocean ridge system. Then he began to think about the ocean floor in relation to the problem of continental drift. That's Alfred Wagner. And finally, he reached a startling conclusion. Maybe Wagner was right. Perhaps the continents do move. Maybe this whole system of mountains is actually moving apart. And you can see on a chalkboard behind him here, he's showing the mantle and he's showing the separation, creating these continents. In 1960, Hess proposed a radical idea. Radical because nobody else was thinking in the same way at the time. He suggested that the process he called seafloor spreading continually adds new material to the ocean floor. In seafloor spreading, the seafloor spreads apart along both sides of the mid-ocean ridge as new crust is added. As a result, the ocean floors move like conveyor belts, carrying the continents along with them. Obviously, you can see right here on the video. It's showing this happening through the process of seafloor spreading. From the center of the core, that hot molten lava on the outside is pluming its way up as it's been heated intensely. You're saying, Mr. Jensen, have we ever been down to the core to actually see this? No, but this is what we're thinking is happening. And as it makes its way up, it's going to spread apart in that convection cycle, and the heat's going to bring it up, and slowly it's going to move apart the continents. There's South America leaving Africa with that seafloor spreading. Now we have this way of going, oh, I think he's right. I think Alfred Wagner just didn't know that the ocean floor looked the way it did. Well, here's one more. Oh, shoot, you can't hear it. let me see if I can better do. Let's go back. Nada. Well, 1 second here. I have to actually exit out of this. Apologize for the delay. Let's play it this way.
According to the continental drift theory, an original supercontinent, Pangaea, began to break into separate land masses about 200 million years ago. The continents gradually drifted to their present location. But how? Many scientists use the plate tectonic theory to explain the drifting of continents, as well as volcanoes, earthquakes, and mountains. According to this theory, continents and oceans ride atop slabs of rock called plates. These huge plates are moved by convection currents in the mantle, a layer of rock extending from the Earth's crust to its core that can actually flow like a very thick liquid. Mantle material close to the Earth's core is very hot, while mantle material further away from the core is cooler and denser. The less dense, warmer material rises as the cooler material sinks, forming convection currents. The same up and down circular movement of material that produces wind in the atmosphere and currents in the ocean also move the Earth's continents. often producing dramatic results.
There we have it. A little video to show you. Now, in this, as we come back to our slideshow, one of the things that we saw as Harry Hess started to say, hey, we've got seafloor spreading. I think Wagner's right. Evidence for seafloor spreading, several types of evidence supported Hess's theory on seafloor spreading. In fact, eruptions of molten material was the first thing. It's highlighted there in green. What does the evidence show? Well, it's this. In the 1960s, scientists found evidence that new material is indeed erupting along mid-ocean ridges. The scientists dive to the ocean floor in Alvin. That's the little submarine you see right here. It's a small submarine built to withstand the crushing pressure 4 kilometers down in the ocean, deep down in the dark. In a ridge's central valley, Alvin's crew found strange rocks shaped like pillows or like toothpaste squeezed from a tube. Such rocks form only when molten material hardens quickly after erupting underwater. These rocks showed that molten material had erupted again and again right by these mid-ocean ridges. Here's a couple of pictures you can see of what these look like. They look like little little circular areas. You can see one here developing off of the coast where you see the bright lava. As it hits that cold water, though, it hardens up and it creates these pillowy shapes. Well, magnetic strips in the rock of the ocean floor is another one. What's the evidence from that? When scientists studied patterns in the rocks of the ocean floor, they found more support for seafloor spreading. Earth behaves like a giant magnet. It's got a north pole and it's got a south pole. And surprisingly, Earth's magnetic poles have reversed themselves many times during Earth's history. We see this because scientists discovered that the rock that makes up the ocean floor lies in a pattern of magnetized strips. The North Pole and the South Pole are poling in different directions, and so all the iron inside tends to line up. Well, depending on which way the magnetic pole is pointing, north or south, it would determine how these magnetic reversals happen. Now, these strips hold a record of reversals in Earth's magnetic field. The rock of the ocean floor contains iron. Iron is what is magnetic. So the rock began as molten material that cooled and hardened. As the rock cooled, the iron bits inside lined up in the direction of Earth's magnetic poles. This locked the iron bits in place, giving it kind of this magnetic memory in a sense.
Scientists found more evidence of ocean floor spreading when special instruments were developed that could detect magnetic stripes in the ocean floor. These invisible stripes formed when the magnetic minerals in lava lined up in the direction of the Earth's magnetic poles. They provide a permanent record of the history of the Earth's magnetism. What scientists learned is that the Earth's magnetic poles have reversed themselves 9 times in the past 3.5 million years, and each reversal is conveniently preserved and recorded by a magnetic stripe. The pattern of these magnetic stripes is identical on both sides of a mid-ocean ridge. So as magma hardens into rock, half moves in one direction and half in the other. Clear evidence of ocean floor spreading.
Another example of how that works. Now, the third and final one, the age of the rocks themselves. This evidence led scientists to look again at Wagner's hypothesis of continental drift because they were drilling for samples. Now, the final proof of seafloor spreading came from rock samples obtained by drilling into the ocean floor. The Glommer Challenger is a ship built in 1968, gathered the samples. The Glommer Challenger sent drilling pipes through water 6 kilometers deep to drill holes in the ocean floor. This feat has been compared to using a sharp-ended wire to dig a hole into a sidewalk from the top of the Empire State Building. Can you imagine how much that would take? Examples from the seafloor were brought up through the pipes. Then scientists determined the age of the rocks in the samples, and they found that the farther away from a ridge the samples were taken, the older the rocks were. The youngest rocks were always in the center of the ridges. This showed, again, another piece of evidence that the seafloor spreading really has taken place. Now, with that being said, subduction at trenches is another thing that we saw. How could the ocean floor keep getting wider and wider? The answer is that the ocean floor generally does not just keep spreading. Instead, part of the ocean floor plunges into deep underwater canyons called deep ocean trenches. At a deep ocean trench, the oceanic crust bends downward. What occurs at trenches? In a process taking tens of millions of years, part of the ocean floor sinks back into the mantle at deep trenches.
So if new ocean floor is being created and the old floor is spreading, the Earth must be getting larger, right? Using radioactive dating, scientists have determined that the oldest rocks on land are almost 4 billion years old, but the oldest rocks on the ocean floor are only 200 million years old. This suggests that the ocean floor is being destroyed as fast as it's being formed. The answer lies in the deepest parts of the ocean, long, narrow, V-shaped crevices called trenches. Found along the edges of the ocean floor near continents or groups of islands, trenches can be over 11,000 meters deep. Many of the deepest trenches are found around the Pacific Ocean. As older ocean floor is pushed away from mid-ocean ridges by new ocean floor, it eventually subducts or slides deep down into the Earth along the trenches. This leaves the size of the Earth's surface the same. The subducted ocean plate is melted by the heat in the mantle. It can then be recycled into new ocean crust at the mid-ocean ridges or rise through the crust to form volcanoes.
Another example of that subduction in trenches there for you. The process of subduction, the process by which ocean floor sinks beneath the deep ocean trench and back into the mantle, is called subduction. Now, as subduction occurs, crust closer to a mid-ocean ridge moves away from the ridge and toward a deep ocean trench. Seafloor spreading and subduction work together. They move the ocean floor as if it were a giant conveyor belt. So as it's pushing that away, you can see this up here in the video playing, it's subducting back into the mantle. New oceanic crust is hot, but as it moves away from the mid-ocean ridge, it cools and becomes more dense. Eventually, as shown in that picture down below, gravity pulls this older, denser oceanic crust beneath the trench. And that's what we see in this area here. Subduction zone, the other side of it. So it's not just expanding the Earth, but as it's spreading apart at a divergent boundary is what we call this, which is just a seafloor spreading. It's moving apart, but it's also going back down and into the Earth, into the mantle at what we call a subduction zone, which is fun to study because that's where we get our really fun earthquakes and volcanoes. Last thing I want you to look at is this right here. This summarizes everything up for us. And it's this right here. The claim that Wagner produced and scientists now agree with is continents on Earth fit together like a puzzle piece, giving the idea that all land was once joined together as a supercontinent called Pangaea, which means all lands. This continent broke up and drifted apart and continues to drift apart even now. The evidence that we're looking at for this, what we see, one, landforms matching up. South America and Africa fit together like a puzzle. Some of those mountains fit together as well. Number two, fossils of plants and animals are found on different continents, oceans apart, to where they couldn't have swam across the water in order to reproduce. Those continents had to have been together at one time. Third one is climate. Climate shows that cold areas like Antarctica have fossils of palm trees, giving evidence that Antarctica was once in a warmer part of the world, must have drifted away at the poles. Number four, the last one we're going to add to this, the seafloor spreading apart at what we now call ridges. We saw A, new magma was being created at ridges. B, the magnetic strips show that the Earth's poles have changed over time, north and south flipped. And C, drilling rocks showed the youngest rocks nearest the ridges and the older rocks as you get further away. So the reason, what is causing the Earth's land to move apart? The answer to this, the thing that we had, the claim, evidence, reason, our claim, continents spreading apart, the evidence, landforms, fossils, climates, seafloor spreading. The reason for this that we think is happening is that we have a convection cycle deep within the Earth where liquid molten rock is coming up from the core to the surface. It's below the crust, and it's creating a conveyor belt or a movement of crust. And that crust, as it moves into the continents, goes back down, cools, subducts into the magma, then it gets warmed back up, and we have what's called a convection cycle. That's what we use for determining if the continents are drifting and what the mechanism was. Hope you enjoyed it today. Hope you learned something as well. We'll see you again right back here, same time, same place tomorrow.